Here is a combined summary of the 4 pages. Transcription-only supervised text spotting aims to detect text in scene images using only text transcriptions without boundary annotations, eliminating the need for expensive boundary annotations. The proposed WeCromCL model conducts atomistic contrastive learning to model the character-wise appearance consistency between a text transcription and its correlated region in the scene image. This approach differs from typical cross-modality contrastive learning methods that focus on holistic semantic correlation. WeCromCL detects anchor points for transcriptions in a weakly supervised manner and uses these points as pseudo-location labels to guide text spotting. The task of transcription-only supervised text spotting is decomposed into 2 stages: weakly supervised text detection and single-point text spotting. The first stage is particularly challenging and crucial for the performance of text spotting in the second stage. WeCromCL formulates this stage as a weakly supervised cross-modality contrastive learning problem and designs a simple yet effective model to learn the character-wise appearance consistency between a text transcription and its correlated region in a scene image. The model achieves this by designing a soft modeling mechanism to learn an activation map by measuring the appearance correlation between a transcription and each pixel of a scene image. The activated region in the scene image is identified as the anchor point for this transcription and is associated with the transcription for contrastive learning to optimize WeCromCL. Without location annotations for text, WeCromCL can still detect each transcription effectively by learning the similar appearance pattern for this transcription among all associated images. The proposed approach outperforms other methods, including TCM, OCLIP, and VLPT, on 4 challenging benchmarks, demonstrating its effectiveness. The contributions of this research include decomposing the task of transcription-only supervised text spotting into 2 stages, formulating the first stage as a cross-modality atomistic contrastive learning problem, and proposing a simple yet effective method for it, called WeCromCL. WeCromCL is a novel transcription-only supervised text spotter that leverages weakly supervised atomistic cross-modality contrastive learning to detect text in images without relying on location annotations. The model consists of 2 stages: detecting an anchor point for each text instance as a pseudo-location label, and conducting text spotting under the supervision of obtained pseudo-location labels. The first stage involves estimating the location for each transcription to serve as pseudo-location labels for supervised learning of a text spotter. This is achieved through a soft modeling mechanism that uses cosine similarity in a projected feature space to estimate the activation map M. The correlation between an image and a text transcription is represented as C equals F M O.I T, where M is an activation map indicating whether the corresponding pixel is associated with the transcription T. The proposed model employs an image encoder and a text encoder to learn latent embeddings for the input image and text transcription. The architecture of WeCromCL is shown in Figure 2, where the image feature and text feature are extracted and then fed into a cross-modality cross-attention module to predict the activation map M and the correlation C. The obtained anchor points are used as pseudo-location labels for optimizing the text spotter in the second stage. WeCromCL uses a character-wise text encoder to tackle the issues of inconsistent transcription lengths and varying character appearances. The image encoder employs BIFPN and deformable transformer encoder to extract multi-scale convolutional features. The model performs cross-modality contrastive learning between the learned correlated visual feature and the encoded transcription feature to optimize all modules jointly. The loss function is defined to maximize the cosine similarity of positive pairs while minimizing the similarity of negative pairs, utilizing a negative sample mining scheme to introduce more challenging negative pairs and enhance the model's performance. WeCromCL is a novel approach for cross-modality character-wise consistency metric learning between image and text, leveraging atomistic contrastive learning to detect correlated regions in images and transcriptions. By minimizing the similarity between negative pairs, the model learns to recognize similar appearance patterns for each transcription, preventing the collapse to a uniform pattern. The anchor point in the activation map is identified as the pseudo-location label for learning the text spotter, instantiated with SPTS and SRSTS v2. Experiments on ICDAR 2013, ICDAR 2015, total text, and CTW1500 benchmarks demonstrate WeCromCL's effectiveness in enhancing modeling robustness and improving text spotting performance. WeCromCL differs from holistic contrastive learning, as employed by OCLIP, by focusing on character-level correlations between a transcription and its visual representation in the image. Ablation studies reveal the crucial role of the character-wise text encoder and negative sample mining scheme in WeCromCL's success. WeCromCL outperforms OCLIP significantly on all benchmarks, showcasing the superiority of atomistic contrastive learning. When used to train SPTS, WeCromCL plus SPTS surpasses NPTS in all evaluation dimensions, particularly excelling in scenarios without lexicons or with generic lexicon. The character-wise text encoder facilitates learning character-level correlations, while the negative sample mining scheme yields large performance gains. WeCromCL represents a significant advancement in weakly supervised text detection, offering a new perspective on leveraging contrastive learning for this task. Its ability to generate accurate pseudo-labels for transcription detection tasks makes it a valuable tool for researchers and practitioners in the field of OCR. The authors propose WeCromCL, a novel transcription-only supervised text spotting method that efficiently generates pseudo-location labels from text-image pairs without annotation cost. This two-stage modeling strategy demonstrates its superiority over single-stage methods like NPTS. The effectiveness of WeCromCL is shown through visual comparisons of corresponding attention maps in the decoder, and its impact on fully supervised spotting methods is investigated. By pre-training SRSTS-V2 on curved synthetic dataset and fine-tuning it on varying proportions of ICDAR 2015 GT and fixed amounts of pseudo-labeled data, the authors observe that WeCromCL can improve the recognition performance of SRSTS-V2, especially when annotated data is limited. Qualitative results of the transcription-only supervised text spotter on ICDAR 2013, ICDAR 2015, total text, and CTW1500 datasets are presented, showcasing the estimated anchor points and sampled points. Quantitative results are also provided in Table 5, comparing the performance of WeCromCL plus SRSTSA with other fully supervised, semi-supervised, and transcription-only supervised methods. The results demonstrate that WeCromCL plus SRSTSA achieves superior performance when compared to other transcription-only supervised methods, surpassing NPTS and TOS by 16.4% and 9.2% on ICDAR 2015, respectively. The authors attribute the improved performance to the efficient generation of pseudo-labels by WeCromCL, which enables the model to learn from a larger dataset without additional human annotation cost. The research proposes a novel approach to text spotting, decomposing the transcription-only supervised text spotting into two stages, and demonstrates the effectiveness and robustness of WeCromCL through extensive experiments on challenging benchmarks. The paper presents a comprehensive overview of recent advancements in scene text detection and spotting, discussing various techniques and algorithms such as Mask Text Spotter v3, TextBoxes++, and ABCNet. These methods leverage deep neural networks to improve the accuracy and efficiency of text detection in images, handling complex text shapes and orientations. The use of focal loss for dense object detection is also covered, along with the development of single-point scene text detectors like SPTS and SPTS-V2, which simplify the text detection process by eliminating the need for anchor boxes or proposal networks. Furthermore, the authors discuss the importance of vision language pre-training for boosting scene text detectors, involving leveraging large-scale datasets and using contrastive learning to learn transferable visual models from natural language supervision. Weakly supervised learning methods, such as Language Matters, are highlighted for their ability to utilize vision language pre-training to improve scene text detection and spotting without relying on strong annotations. The paper also addresses the limitations and future work in this field, emphasizing the need for more robust and efficient algorithms that can handle diverse text shapes, languages, and environmental conditions. It suggests integrating multiple modalities, such as audio and vision, to further enhance text detection capabilities. Additionally, the paper discusses the development of a novel text spotting system, WeCromCL, which adapts the SRSTS model to improve performance using weak supervision. The system consists of an image encoder, anchor estimator, sampling module, and recognition module, and has been modified to drop the detection branch, incorporate practical techniques from Deep Solo, and use focal loss for optimizing the anchor estimator. An ablation study comparing the pseudo-label quality generated by WeCromCL with other weak supervision methods, such as OCLIP and NPTS, demonstrates the efficacy of WeCromCL in generating high-quality pseudo-labels for text spotting tasks. The authors present a comprehensive evaluation of their proposed WeCromCL method, focusing on the spotting task on the ICDA ART 2015 dataset. They compare the performance of different pseudo-label generation methods and ablation conditions, showcasing the effectiveness of WeCromCL. The impact of anchor quality on spotting results is investigated, demonstrating that the accuracy of WeCromCL is comparable to using ground truth anchor points. The performance gap between fully supervised methods is attributed to pseudo-label accuracy and positional supervision method. The authors also present activation maps generated by the model, which demonstrate WeCromCL's ability to handle complex cases. A novel approach is presented to leverage a transcription-only supervised method for achieving satisfactory performance. This method utilizes a deep neural network to locate text regions within images when given a text query. The process involves enlarging the input image to ensure accurate location of the queried text, regardless of its size or clarity. The visualization of text spotting results on 4 benchmarks demonstrates the effectiveness and robustness of this transcription-only supervised text spotter.